Yeah. Yeah, dear students, continuation to the previous class. In the first block, I'm going to start the fifth unit, that is the elimination reactions. What are the elimination reactions? In this unit, what we are going to learn is what are the elimination reactions and a classification of elimination reactions and a mechanism of some elimination reactions and orientation in elimination reactions, and sometimes substitution reactions are competing with the elimination reactions. That's why elimination versus substitution reactions are going to be discussed here. Then first you coming to what are elimination reactions. Elimination reactions are removal of removal of groups, two groups or atoms from a molecule. It produces the unsaturated product or a cyclic product or a reaction intermediate. Such reactions are known as elimination reactions. From a molecule, we are removing two groups. That results, it is transforms to a unsaturated compound or a cyclic compound, or it is a reactive intermediate or reaction intermediate, is known as elimination reaction. Now, elimination reactions are classified into different types. The first one, alpha elimination reaction. What is alpha elimination? If two groups or atoms are removed from the same atom, is known as alpha elimination. It is also known as 1-1 elimination or two group elimination from the same center. That means at the first position we are eliminating two groups or atom from the same position, that leads to the formation of some intermediate. This is known as alpha elimination reaction. Example for chloroform to carbene conversion. Chloroform to carbene conversion. Here you take the chloroform that is treated with base. That base is reacting with chloroform. It first eliminates the proton. It forms a carbon ion. After formation of this carbon ion, removal of another chlorine, that leads to the formation of chlorine is removed as a chloride ion, Cl minus. Therefore, it leads to the formation of neutral reactive intermediate that is called dichlorocarbene. Okay, that is known as alpha elimination reaction. Next, beta elimination reaction. These are all known as elimination of two groups or atoms from adjacent position or 1-2 position are known as beta elimination. In these two groups are lost from the vicinal or adjacent positions. These reactions lead by ultimately to form the a multiple bond, that is unsaturated bonds are generated after elimination. One of the group is lost without. Yes, two groups or atoms are eliminated from the 1-2 position are known as beta elimination. Here some example is given. A generalized example, Z and X. Z is the electrofuse and X is the nuclear fuse. Right. First, the nuclear fuse is eliminated with a sigma pair of electron as X minus. Simultaneously, the carbon Z electrofuse bond is taken by the carbon, that is donated to the system carbon compound, that leads to the formation of carbon-carbon double bond. At the same time, it leads to the XZ is the eliminated product. Elimination is takes place, that leads to the formation of an unsaturated compound. One of the group is lost without electron constituting the bond, and the other is lost with the electron pair constituting the bond. There are known as electrofuse and nuclear fuse respectively. Here, this group is leaving with electron pair. This is called nucleophuse. Here, this Z is leaving without electron. This is known as electrophuse. It is losing its electron. It is gaining. The X is gaining electrons. Right. The carbon from which nucleophuse is lost is called alpha carbon, and the form and that from which electrophuse is lost is beta carbon. In majority of the elimination reactions, hydrogen is the electrophuse. In most of the cases, we see that hydrogen is the electrophuse. Some of the examples are given for the beta eliminations are base catalyzed dehydrohalogenation, alkyl halides, dehydrohalogenation of alkyl halides. HX is at the center present in the carbon compound is treated with base. The first base is abstracted the proton, H plus ion. This pair of electrons are donated to the carbon. Simultaneously, X minus is released as HX is generated along with the our and the required compound, unsaturated compound. The acid catalyzed hydration of alcohol, dehydration of alcohol that leads to formation of simply it is treated with acid. The protonation of acid is takes place on the OH. Slowly the OH is eliminated. This is called a nucleophuse. Then carbon hydrogen bond pair is donated to the carbon to form the double bond. This is the hydrogen is the electrophuse. OH is the nucleophuse. Debromination of 1 comma 2 dibromoalkane catalyzed by iodine or zinc metal. Like here, 1,2 dibromo compound is there, which is treated with iodine or zinc. It is undergoing debromination, that is Br2 is eliminated from the molecule that leads to the formation of carbon-carbon double bond compound. And often degradation of quaternary alkyl ammonium hydroxides. Quaternary ammonium alkyl quaternary alkyl ammonium hydroxides, which is treated with a simple base. Then slowly a tertiary amine is trialkyl tertiary amine is eliminated that leads to the formation of an unsaturated compound. Sometimes a group may be lost from a heteroatom. Sometimes the groups may be lost from the heteroatom. For example, here acetate of dialdoxane. Acetate of aldoxane. Here the group acetate group is eliminated from the nitrogen. Then that leads to the formation of nitrile, alkyl nitrile compound is generated. Next to omega elimination. Third type of eliminations are omega eliminations. Generally, these reactions are this reaction is takes place. The electrophuse and the nucleophuse eliminated from the more than uh, two sigma bonds separated positions. That is known as omega elimination, or if you count the positions alpha, beta, gamma, delta, and omega. Electrophy is eliminated from the omega position, and nucleophile is eliminated from the first position. Now, the 1 comma 5 elimination reactions are known as omega elimination reaction. Here, the example is given, that is Dechman reaction. In the Dechman reaction, electrophiles and nucleophiles are lost from 1 to 2 comma 1 comma 5 atoms. Next, mechanism of beta elimination reactions. What is the mechanism of beta elimination reaction? Beta elimination reaction mechanism can be explained in the three different pathways. One is the E1 elimination and the E2 elimination, E2 elimination, and E1 E2 elimination, E1 CB mechanism. In three mechanisms, we can explain the elimination reactions. Now, coming to the E1 elimination. In that E1 elimination, you see that E1 elimination. What is the E1 elimination? Elimination unimolecular mechanism. Elimination unimolecular mechanism. In this, if you see that below example, tertiary butyl halide is treated with base that leads to the formation of isobutylene. It is complete elimination of HX that leads to the formation of a double bond on the molecule. Then the tertiary butyl halide is converting into isobutylene. From the tertiary butyl halide in the presence of base, which is treated with base, first it will abstract the proton from alpha second position or beta position. Then first it is converting into water. Then a negative charge is generated here. This negative charge is doing to the carbon to form the carbon-carbon double bond. Simultaneously, this X is eliminated. But this reaction is proceeds through the formation of a carbocation intermediate. Carbocation intermediate. Look at here. The reaction exhibits first order kinetics. The rate of reaction is directly proportional to tertiary butyl halide and independent of the concentration of whatever the base we are used, OH or KOH, whatever the base we are used. Therefore, the unimolecular reaction even mechanism is proposed for the reaction. First, this alkyl halide, slowly, due to the field effect, this pair of electrons are more towards the X. Therefore, this halogen bond is readily dissociated. That leads to the formation of X minus. This is the slow and rate determining step. In this rate determining step, only the concentration of substrate is depends on the rate. Now, after formation of this carbocation, here the two pathways it can take. One is the elimination reaction and one is the substitution reaction. If it is a substitution reaction, this is the unimolecular substitution reaction, nucleophilic substitution reaction. Or if it is the elimination reaction, this is the even elimination, unimolecular elimination reaction. Suppose if this carbocation is upset the adjacent beta carbon hydrogen bond pair of electrons, then elimination of proton leads to the formation of that even elimination product. And if it is undergoing the substitution reaction with base, that will leads to the formation of alcohol. In these two steps of mechanism, the first step involves the heterolysis of carbon halogen bond. This is the rate determining step. The resulting carbocation in the fast step loses H plus ion. That H plus ion is accepted with base like OH, like water or ETOH. The overall rate depends on the formation of carbocation, which again depends on substrate concentration. If the base function as a nucleophile, the reaction is called nucleophilic substitution reaction. Instead, if the base is acting as its own base, it abstracts the proton, then that leads to the formation of unsaturated product. Now, the base is acting as nucleophile that is involving the substitution reaction. The substitution reaction follows the substitution unimolecular nucleophilic substitution. That is SN1 mechanism it follows. An elimination reaction is always accompanying with the nucleophilic substitution reaction. All substrates capable of forming stable carbocations like benzylic, allylic, tertiary carbocation undergo elimination reaction by even mechanism. The substrate with the different nucleophuses like tertiary butyl chloride, tertiary butyl bromide, tertiary butyl iodide, giving same carbocation gives same mixture of elimination and a substitution product. However, they react at different rates. In the even reaction, rearrangements characteristic of carbocation have been observed. And if you observe the example here, tertiary butyl alcohol, it is the even reaction, acid catalyzed dehydrogenation of reaction. In this reaction, fast elimination of proton that fast protonation of OH group in the tertiary butyl alcohol that leads to the formation of protonated tertiary butyl alcohol, which is dissociated to produce carbocation and water. This carbocation eliminates the proton rapidly that leads to the formation of unsaturated product. Stereochemistry of even reaction. Stereochemistry of even reaction. Uh, Even reactions are not stereospecific. Even reactions are not stereospecific. Two diastereomers reacting to the same carbocation, carbonium ion, uh, it forms stereochemically identical products. Therefore, it is not yet stereospecific. For example, if you take the cis and trans dialkyl cyclohexyl chloride undergoes elimination reaction through the formation of carbonium ion or carbocation from the same mixture of 1 alkyl and 3 alkyl cyclohexene. 1 alkyl and 3 alkyl cyclohexene. Look at here, this is a cis isomer and this is the trans isomer of 2-alkyl cyclohexyl chloride. It is a trans. Now, which is on protonation, which is on treating with the elimination reaction conditions. It is undergoing the CCl bond dissociation that leads to the formation of carbocation. In the both the cases, cis and trans, we know that those two are the diastereomers. Those two diastereomers are producing the same kind of intermediate. Then it is under further it is undergoing elimination reaction that leads to the formation of a mixture of products, that is 3-alkyl cyclohexene, 1-alkyl cyclohexene. E2 elimination are bimolecular mechanism. Base catalyzed reaction of ethyl bromide forming ethylene is an example. That is the ethyl bromide which is treated with a base that leads to the formation of ethylene. The reaction exhibits second order kinetics. The rate of reaction is directly proportional to the concentration of ethylene bromide and concentration of OH minus. Now, in this reaction involving a transition state, in the transition state, um, incoming group and outgoing group both are partially attached with the reaction center. That leads to the formation of 1, 2, 3, 4, 5, 5 center transition state is established. Now this leads to after complete elimination of this bromine and H plus ion from the molecule, that leads to the formation of unsaturated compound. This removal of OH plus and Br minus is uh, uh, anti-transfer that should be exist in the anti to each other. Hydrogen and bromide in opposite to each other, then only they can easily remove. E2 mechanism is also known as one step or concerted mechanism. A stage midway between the reactants and products is called E2 elimination state. In the E2 transition state, attack by base on the beta hydrogen formation of 5 bonds between the alpha carbon and beta carbon and the departure of bromine minus occur simultaneously. The beta hydrogens and the nucleophiles are arranged trans are anti to each other. Trans and anti to each other. Here you see this trans and anti to each other. The negative charge is separated over the transition state. The rate of reaction depends on the rate of formation of E2 react transition state, which again depends on the concentration of the substrate and reagent. Now, what is here kinetic isotopic effect? What this effect? How this is affecting the E2 elimination reaction? The CH bond is more easily broken. We see that there is a molecule which is undergoing the elimination reaction where the CH bond containing hydrogen elimination is important for that reaction. Okay, that can be easily broken. Suppose the CD bond is there. It is somewhat takes higher energy when we compare to the C energy for cleaving up the CD bond. Okay, the bond between the beta carbon and the hydrogen is broken in the slow and rate determining step of E2 mechanism. When the beta hydrogen is substituted with deuterium, and the rate of reaction of compound containing CH and CD bond will be different. That is KH by KD will be 3 to 11. The rate difference. This variation in the rate of reaction is called as kinetic isotopic effect. All substrates reacting through all substrate reacting through E2 mechanism exhibits kinetic isotopic effect. Next, this reaction, we are considering one reaction, uh, debromination. Debromination, it is treated with iodine. Iodine is interacting with bromine. Simultaneously, the bromine is act as a electrophuse. The bromine is eliminated. Bromine carbon bond pairs of electrons are donated to the substrate that leads to the elimination of bromide ion. That IBr and B bromide ion both will combine to produce bromine and I minus. Right? That means the catalyst is regenerated, and here C double bond C, an unsaturated product is generated. Next, solvent-lysis reaction. In many reactions, solvents are used as nucleophilic reagents. No other base is used. These are commonly referred to as Salvay's reaction. If you take a nucleophilic reagent in a solution or in a solvent, okay, there is a reaction between the solvent and nucleophilic reagent. No other base is used. There is no need of using other base. These are commonly referred as solvent reaction. Common solvents are water, ethanol, and acetic acid. These cause hydrolysis, ethanolysis, acetolysis, respectively, of the substrate. In this solvolysis reaction, elimination products are formed. These elimination products may be either even solvolysis products or E2 solvolysis products. Since the solvent is used in larger extent, its concentration will not vary materially during the reaction, and the kinetic data alone cannot decide between E1 and E2 mechanism. A small quantity of the conjugate base of the solvent is added. The reaction mixture, when there is no change in the rate of reaction, it is even solvolysis. On the other hand, in E2 solvolysis, suppose the rate are increasing or decreasing, that reaction is known as E2 solvolysis reaction. The rate is increasing in the case of E2 elimination reactions. If you add any conjugate base to the reaction mixture, the rate will be increased. In such condition, we can understand that the reaction is E2 elimination reaction. Next, stereochemistry of E2 reaction. E2 reactions are highly stereospecific. They proceed through the syn-periplanar or anti-periplanar transition state. In both these transition states, the nucleophiles alpha carbon and beta carbon are electrophiles and coplanar in the syn-periplanar transition state. The electrophiles and nucleophiles are in cis orientation. In the anti-periplanar, the transition state that is arranged as anti orientation. The elimination reactions takes place through syn and anti-periplanar transition state, are referred to as cis and trans elimination respectively. Anti-periplanar transition state is referred to syn periplanar transition state for the A2 elimination reaction. If you see this here, the below two diagrams represents that syn periplanar transition state and anti-periplanar transition state. After observation of the reaction mechanism of several reactions, anti-periplanar transition state is preferred because there is no steric strain. The elimination is very much easier from the molecule. The elimination of the two groups or atoms from the molecule is very easy. Then that is the reason anti-periplanar transition state is preferred to syn-periplanar transition state. Next, it is the example base catalyzed. The stereochemistry of the major products in heat elimination reaction can be predicted by the arrangement of substituents in the anti-periplanar transition state. Some of the examples are illustrated here. The base catalyzed dehydrobromination of 1, 2 dibenzoyl 1, 2 dibromide an intermediate. Like this one is the dibromo mesomer that is adjusted in the Newman projection formula, that is rearranged to anti-periplanar structure. In that anti-periplanar structure, the elimination of hydrogen and bromide, that is hydrogen bromide, is eliminated. Then it leads to the formation of a cis-olefin as the major product. Next, in the case of active isomer of the same compound, same structural compound, then it is arranged to anti-periplanar that leads to the formation of trans product. In the first orientation, gives the cis product, active gives the trans product. Meso gives the olefin, cis olefin, then other active isomer gives the trans olefin. Active isomers react 7 times faster than the meso isomer. Why? Because here look into that. In the mesoisomer, you look into this. Here the two bromides are adjacent to each other. The CO pH group, bulkier groups are adjacent to each other. There is a steric repulsions. The approach of base is somewhat difficult in such. Due to that reason, it undergoes the slow reaction. In the case of, we look into that, the bromine, however, the bromines are adjacent to each other, the remaining bulky group, benzoyl groups are anti to each other. In such condition, the elimination of the HBr is very much easier. Due to that reason, the active isomers which is involved in the elimination reaction is 7 times faster than the isomer which is involved in the elimination, that is the meso isomer. Next, base catalyzed dehydrobromination of 1 bromo 1 comma 2 diphenyl propanes. Yes, 1 bromo 1 comma 2 diphenyl propane with two dissimilar asymmetric carbons, two dissimilar hydrocarbons. The compound exists as four isomers. The compound exists as four isomers. The two pairs of diastereomers, whereas the plus or minus erythro and plus or minus 3 isomers. First, you come into the erythro isomer. The erythro isomer is this one. In this erythro isomer, the when the vertical line both ends are occupied by the two phenyl groups, in the horizontal lines, bromine and methyl groups are same side. Now, this is the erythro isomer. In that erythro isomer, adjusted to anti-periplanar structure by using the Newman projection formula on the elimination of hydrogen bromide. First, it is the base is interacting with proton that eliminates as water, and the simultaneously elimination of the bromide ion that leads to the formation of cis olefin is the major product. That is, yes, erythro produces the cis product, and trans produces the major product by the active isomer. Here, the 3 isomer is producing major product as trans olefin. Same mechanism. Next. Right. Some of other examples. Yes. Here erythro this is also erythro produces the cis isomer, 3 isomer produces the trans isomer. Right. Iodine catalyzed debromination of 2 comma 3 dibromobutane. This is the dicomma or 2 comma 3 dibromobutane. In this case, 2 comma 3 dibromobutane, which is undergoing the elimination of bromine, that leads to produces the 2-butene as the product. The 2-butene may be existing in two geometric isomers, trans and cis. Now, which one is producing the major isomer? Is meso isomer produces the trans isomer, and active isomer is produced the cis isomer. That can be explained by taking the Newman projection formula. Here, the meso isomer is arranged into Newman projection formula. Later, it is adjusted to the anti-periplanar structure. Then iodine is interacting with bromine. Simultaneously, it produces the I minus and Br2 that leads to formation of trans isomer. Similarly, active isomer leads to the formation of cis isomer. In the cis elimination, E2 reaction in a majority of cases, trans elimination is a general rule in cyclic systems. In cyclic compounds where anti-periplanar transition state is not possible, trans elimination rule is violated, and therefore they undergo elimination through the syn periplanar transition state. Trans 2, 3 dichloro norbornane undergoes E2 reaction much faster than the cis isomer. This is the trans isomer, syn periplanar transition state. On the other hand, the cis isomer cannot react through the either syn periplanar or anti-periplanar transition state, and therefore undergoes elimination very slowly. Similarly, cis 2 bromo 2 deutero non-bornane undergoes facilibase catalyzed elimination through the syn-pyridine transition, yielding a product completely free from the deuterium. Okay. Next, even elimination, that is the unimolecular conjugation based mechanism, even CB mechanism. In this reaction mechanism, elimination reaction takes place through the formation of the even CB. Conjugate base is formed by of the substrate that is undergoing the that is leading the mechanism for the formation of unsaturated product. An example is 1,1-difluoro, 2,2-dichloroethylene. In this, an HF is eliminated. Uh, the hydrogen and fluoride both are anti to each other. That leads to the formation of 1,1-difluoro, 2,2-dichloroethylene. Next, in that trifluoro-dichloroethane is the fast elimination of proton that leads to the formation of carbon ion. That carbon ion is rearranged to elimination of proton to produce the unsaturated 1,1 difluoro 2,2 dichloro, with 1,1 dichloro 1,2 dichloro. The olefin is generated. Right. That my suggestion is the 1,1 dichloro 2,2 dichloro ethylene is generated. The base rapidly removes proton from the beta carbon, resulting in the formation of carbon ion, which loses fluoride ion nucleophase. That is, fluoride ion is act as a nucleophase in the rate determining step. The rate of reaction therefore depends on second step, which depends only on the concentration of a conjugate base of the reagent. Kinetically, even CB reaction and E2 reaction are quite similar. A distinction can be made uh, between even CB and E2 reaction very easily by means of labeling experiment. The first step in even CB mechanism is reversible. Hence, when the reaction is carried by ET minus in ETOD, the intermediate carbon ion should pick up, determine the deuterium, and the recovered substrate will contain deuterium in beta position. On the other hand, deuterium incorporation should not be observed if E2 mechanism is operates. Next to pyruvatic reaction, or this is also called pyruvatic elimination reactions. Pyrolytic conditions. In pyrolytic reactions, other than heat, no reagent is or solvent is used in this reaction. These are all ionical concentrated and first order reactions. Pyrolytic reactions are all ionic, concerted, and first order reaction. Pyrolytic eliminations are unaffected by either free radical initiators and inhibitors. These reactions proceed through the cyclic transition state, the pyrolysis of alkyl halide esters, xanthate esters, and tertiary amine and oxides belong to this group. Here, pyrolysis of esters. On the of the pyrolysis of ester at 400 degrees centigrade, the ester will be hydrolyzed to olefin or ester. Next, pyrolysis of alkyl halides. On pyrolysis of alkyl halides at 400 degrees centigrade, that leads to the formation of olefin and HX. Pyrolysis of alkyl S-methyl xanthate. This is also known as Chugev reaction. In that, this is Chugev reaction. The Chugev reaction, xanthate, alkyl S-methyl xanthate. Alkyl S-methyl xanthate is heated at 100 degrees centigrade. That leads to the dissociation and which forms the olefin along with the some CH3SH and thioketene product. Next, stereochemistry of pyrolytic reactions. Yeah, these are highly stereospecific. These reactions are some co-prearrangement N oxide, pyrolysis of tertiary amine N oxide, co-prearrangement. These reactions take place at relatively lower temperature. In this, if you see this, a tertiary amine N oxide, which is treated with 100, treated at 100 degrees centigrade, the olefin is generated. Dimethyl hydroxamine is generated. Next, stereochemistry of pyrolytic reactions. Pyrolytic reactions are highly stereospecific and involves syn-periplanar transition state. Following are some examples of pyrolytic reactions of diastereomer substance. Pyrolysis of S-methyl 1,2 dimethyl xanthate. Xanthate. This part is known as xanthate. Now, which is written as like this tetraisomer. In the tetraisomer, if we are arranging this into a new projection formula, a syn elimination is takes place in the pyrolytic reactions that leads to the formation of erythroisomer, leads to the formation of transisomer. Next, three isomer, it leads to the formation of cis isomer. Erythro leads to the transisomer, threo leads to the cis isomer. Pyrolysis of 3-phenyl 2-butyl diphenyl N oxide that can be represented as erythroisomer. This erythroisomer, no need to appear in anti-periplanar. Syn-periplanar will give the reaction very smoothly that leads to the formation of cyclic transition state. Or formation of that cyclic transition state that will be broke down that leads to the formation of olefin. Three isomer, the cyclic transition state. This three isomer leads to the formation of cis isomer. Next, pyrolysis of 2-deutero 1,2 diphenyl ethyl acetate. This is erythroisomer. This erythroisomer leads the syn elimination takes place. That more stable product is cyclic transition state leads to the more stable product. That is phenyl group is the anti-orientation. That leads to the formation of alpha deuterotranstilbene product is generated. Next, three-isomer leads to the formation of trans-isomer. Next, orientation of elimination reaction. The entire elimination reaction, the important topic is how these elimination reactions are oriented. That means sometimes we are expecting some product, eliminated product, but it leads to the formation of one product. Okay, that is decided by the orientation of elimination reaction. Elimination reactions of unsymmetrical substrates generally leads two or more products. Two empirical rules govern the orientation of these reactions. This orientation can be explained by using two rules. One is the CGF rule and another one is the Hoffman rule. What is the CGF rule states? CGF rule eliminates CGF rule in the elimination reaction of an unsymmetrical substrate yield more substituted ethylene is the major product. More substituted ethylene is the major product. Suppose the olefin bearing large number of alkyl group is the more substituted olefin. The rule is applicable to both E1 reaction, E2 reaction, or neutral substrates like alkyl halides, esters, and alkyl sulfonates. For example, there are two beta carbons in 2-methyl 2-chlorobutane. Loss of proton from either beta carbons due to two isomeric olefins, that is in E1 solvalysis 2-methyl 2-chlorobutane, 2-methyl 2-chlorobutane is obtained as the major product, right? Butene is the major product. 2-methyl 2-butene is the major product, 80%. This is the mechanism. And the next exception of the even reaction. What are the exceptions? There are two major factors which cause exceptions to CH rule. Size of the substituent on beta carbon. When a group bulkier than the methyl group is present on beta carbon, steric factor stabilizes the CH product. For example, in even evaluasis, 2 chloro 2 comma 4 comma 4 trimethyl pentane CH product is the major product. Pentane is the major product. Look at here the 2 comma 2 chloro 2 comma 4 comma 4 trimethyl pentane that leads the formation of the major one is 2 comma 4 comma 4 trimethyl 1 pentane is the major product and minor product is 2 comma 4 comma 4 trimethyl 2 pentane, that is the CGF product. It is the more substituted product and this is the less substituted product. This is the exception. CGF product is destabilized due to the significant steric influence between the tertiary butyl and methyl group. So, situated is to each other. Similar trends is observed in the reaction between 2-bromo, 2 comma 4 comma 4 trimethyl pentane and a strong base. In this E2 reaction, the base would find it's easier to attack more exposed beta hydrogen, sterically less hindered. The hydrogen is more favored to attack the base than the sterically more hindered beta hydrogen, leading to sterically more stable 2 comma 4 comma 4 trimethyl 1 pentene as the major product. Increasing the size of base. A large base will find it easier to attack sterically less hindered beta hydrogen, leading to the CGF product as the major product. Following results will be we have encountered. Right, 2-methyl 2-bromobutene, which is treated with the tertiary, sorry, uh, ethoxide ion that leads to the formation of E2 reaction. The CGF product is tri-substituted and this is the less substituted CGF product. The base size increases, the CGF product formation is gradually decreases. Next, Hoffman rule. Hoffman rule is applicable to ionic substrate like quaternary ammonium salts, sulfonium ion salts. According to Hoffman, the elimination of unsymmetrical oxygen salts, olefin bearing smaller number of alkyl groups is the major product. For example, the base catalyzed elimination reaction of ethyl diethyl and propyl ammonium salt predominantly forms ethylene. Here, more acidic beta position is this one. This hydrogen is more acidic, and this is the less acidic, which is untreated with base. That 96 percentage is the formation of simple olefin, that is ethylene, and 4% is allyl. Allyl, allyl, allyl. It are 1 propene. The results can be explained by the relative acidities of hydrogen on beta prime carbons. The positive charge nitrogen influences the acidity of beta and beta dash hydrogens to the same extent, but the plus inductive effect of methyl group decreases the acidity of the hydrogen on beta prime position or beta prime carbon. Therefore, the base attacks more acidic beta hydrogen, gives ethylene as the major product. This is the mechanism. The base is attacking here more prominently than the beta prime position that leads the formation of major product. On the other hand, when an electronegative group like aryl, carbonyl, nitrile, nitro, like groups are there present on the beta carbon, often product is the major product. Aryl group and carbonyl group, nitrile group or nitro groups are present. It leads to the formation of more amount of Hoffman product than the CGF product. The electronegative groups increases the acidity of beta prime carbon hydrogen, beta carbon hydrogen bond or hydrogen acidity becomes increased. Therefore, the base attacks the beta prime hydrogen, yielding the predominantly CGF product. Moreover, CGF product is stabilized by the conjugation. Next, elimination versus substitution. As we discussed previous, elimination reaction proceeds through the formation of carbocation. In the E1 reaction or E2 reaction, always accompanied by the SN1 reaction and SN2 reaction respectively. The extent of elimination and substitution from a substrate is influenced by the some factors are given below. Structure of substrate. In general, with increasing branches of the chain in the reactant, the proportion of the elimination products also increases. In unimolecular reaction, E1 reaction and SN1 reactions are competing, and the common intermediate is the carbonium ion. Formation of carbonium ion releases steric strain in the substrate by increasing the bond angles and from 108 109 to 28 degrees to 120 substitution 120 degrees substitution reaction reintroduce the steric strain against appear. On the other hand, elimination reaction does not alter the bond angles in biomolecular reactions. Elimination domination due to the formation of more stable, highly substituted olefins. Nature of base. A good nucleophile need not be a good base and vice versa. The basic strength of a reagent depends on its ability to accept a pair of electron or accept a proton. On the other hand, nucleophilicity of reagent depends on its ability to form bond with a carbon atom. Following is the order of basicity and nucleophilicity of some reagent. Basicity OH minus SH, acetyl and chloride, iodide water. Nucleophilicity that it becomes reverse SH minus I minus OH minus Cl minus acetate minus and water. This is the order it follows. Stronger base promotes elimination reactions in biomolecular reactions, for example, with I minus, a strong nucleophile and a weak base. Substitution predominates. Further, increases in the concentration and basic strength in molecular mechanism changes to bimolecular mechanism. Polarity of solvent. Less polar solvents Less polar solvents promotes bimolecular reaction by solvation. This effect is more pronounced with E2 reaction than the SN2 reaction. Thus, in less polar solvents, as E2 by SN2 in ratio increases. Effect of temperature. The energy of activation of an elimination reaction is usually higher than that of the corresponding substitution reaction. Therefore, high temperature favors formation of elimination products from the substrate. Substituents on beta carbon. Electron withdrawing group on beta carbon like nitro, cyanide, and keto groups are there, increasing the acidity of beta hydrogen and therefore favors the elimination reaction. Okay, this is about the elimination reaction. We will continue next class. Thank you.